Okay, so we talked about the direction and magnitude of a force on a wire that is carrying a current, and this current, this wire, feels a force when it goes through a magnetic field. Now we are going to do the same. We are going to study the force, but now instead of studying the force on a current, now instead of having current, which is a flow of many charges, I'm going to study the force on a single charge. Okay, so the problem that the drawing that you see here is similar to the one that we had seen before for the current. Now I have here north and south pole, so the magnetic field is pointing to the right. So I'm saying that this is similar to this problem that we saw before, north and south pole, magnetic field is to the right. In this exercise here, what we had was the current. The current was going towards into the page. Okay, and what is the current? What is the direction? The current is the direction of many positive charges. Now that's the convention. The direction of the current is of the motion of the positive charges. Okay, so in this new scenario here, we have the magnetic field to the right, and we are going to send charge, a positive charge, towards this magnetic field. Okay, so you imagine that you have this positive charge at the tip of your nose, and you throw it into the screen, you throw it into the page. Okay, so that this positive charge goes through the magnetic field. So what is the direction of this positive charge? What determines the direction of this positive charge? The velocity. Okay, it's velocity. So I have the velocity of this positive charge going towards the page. So you have here this V indicating the velocity, okay, going towards the page. What is going, and this particle, this positive particle is going, this positive charge will feel a force. What is the direction of this force? Well, you're going to use the same rule, that we use for the current. What was the story? The direction of the current. We put our four fingers. Well, now is the direction of the velocity of this charge that we are going to use our four fingers for. Now, so the direction of the velocity of this charge is towards, now it's into the page, passing through this magnetic field. So my four fingers is going to be pointing to the page, to the screen. How about the palm? The palm is going to be pointing to the right. And so I get a force pointing down. Exactly the same idea as in this case. No? Current going into the page, so four fingers into the page, palm to the right, and then force pointing down. Okay, so we employ the same rule. The only difference now is that instead of having current, we have a single charge. So we point our four fingers in the direction of the velocity of this charge. Okay, now the issue is we could throw not a positive charge, we could choose to throw a negative charge. And what do we do if we throw a negative charge with a certain velocity v? Well, again, you follow the same rule, but remember, current follows, the direction of current is the direction of positive charge. And if you are throwing a negative charge, what you have to do at the end, once you get to the force, in our case here, force pointing down, you think to yourself, oh no, but I was playing with a negative charge. So everything is opposite, meaning the direction of the force, you just have to flip it, and the direction will be pointing up. Okay, so our positive charge, once it gets into this region of the magnetic field, it feels a force pointing down, so it gets deflected down. The negative charge, once it reaches the region of the magnetic field, it feels a force but in the opposite direction. So this force is pointing up, so it will be deflected up. Okay, this is for the direction. Okay, so the direction of the force, what you have to look at, the direction of the velocity, that is your four fingers, the direction of the magnetic field, that is pointing, that's the palm that is going to indicate, and then the thumb for the force. If it's positive charge, everything is exactly equal to what we did for current. If it's a negative charge, all that you have to do at the end is to flip the force in the opposite direction of whatever the positive charge would have. Okay? How about the magnitude? The magnitude is given by this equation. How do we get this equation here? Well, let's write the equation that we had for the current. So the equation was I, current, length of the wire within the magnetic field, and the angle, sine of the angle between the current and the magnetic field. Okay, what is current? Current is a lot of charge and charge per time. That's the definition of current. Then multiply by L, V, and sine of theta. Well, now I see length divided by time. And what is that? Now the length, the part, the length of the charge moving through the magnetic field, now that piece, um, that piece where the charge is going to fill the magnetic field. Now, so length divided by time is going to give us the velocity, the magnitude of the velocity, the speed of that charge, of those charges. Now we have here still many charges. Okay, so N, so the force is NQ, all the Q's are going in this current, the speed of this charge, B, and sine of theta. Well, but if I have a single charge, N is 1, and then I get my equation, Q, V, B, sine of theta. Okay, so this is the equation for the magnitude of the force that a charge will feel once it goes through the magnetic field. Okay, so this equation is for the magnitude of the force, so this is going to be valid if the charge is positive, if the charge is negative. Now, so this equation is only going to give us a number, it's not going to give us direction. And what is this angle theta here? This angle theta is now the angle between the direction of the velocity and the direction of the magnetic field. Okay, that's the end. What we are going to do in the next videos is to solve some problems for this kind of scenario.